One of the issues of having high correlations between input variables is collinearity. It can lead to a distortion in the beta coefficients. These are the regression coefficients. And what happens as the degree of collinearity increases, we have increasing problems. So here, if we have correlations positive or negative in these ranges, you'll get a bit of distortion in your beta coefficients. And as you get stronger, plus or minus 0.75, you get more distortion. And if you get plus or minus 0.9, you get a lot of distortion in the beta coefficients. Now, these levels usually don't cause problems with your data mining software being able to work. But if you get really high numbers, sometimes you get 0.99, 0.98, sometimes data mining software will not even let you run. It can't invert the matrix and do the math. And so that's a problem beyond this issue with distorting your betas or having unstable betas. I thought to help you see this by example, I prepared two examples. One where we sort of violate the rules and one where we don't. In this particular example, let's assume that we're trying to predict weight loss. And we have been tracking how well people have been staying on their diet and how well they exercise. We also know what their household income is like, whether they have been using a diet support group, and how many work hours per week they work. Now, if you look at the correlations with the input variables with weight loss, you can see there's a lot of information here. There's strong correlations between diet and exercise with weight loss, and there's also a strong negative correlation between hours worked per week and weight loss. Perhaps as people are working more, they're not finding time to exercise and so forth. Now, you can see in the scatter plots that if this being weight loss, that diet and exercise have very positive correlations. So what you see numerically here, you can sort of see visually here. And then as we get down to household income, there is some correlation, but it's not as strong. And then here, when we get down to our hours worked per week, there's this negative correlation between hours worked per week and weight loss. So that just sort of gives you a quick overview of what the data is and what the correlation table looks like. Now, you might recall that when we start getting up to around 0.75 positive or negative correlations, like this relationship between diet and exercise, we're going to have a bit of distortion in our beta coefficients. And we also have this one here that's not quite up there. So I went and ran a series of models where I put all of these input variables to predict weight loss. And this was the result of that. And I found that diet and exercise were statistically significant in their relationship to losing weight. And work hours per week almost got down to 0.05, and these were not statistically significant. So I went and gradually dropped out terms. So I dropped out the statistically non-significant, these bottom two, household income and support group. And then I kept dropping variables because we're not really having really strong collinearity problems, that our betas are pretty stable. So for example, here's what our beta coefficients are in the model where all of these terms are in here. As I dropped out these two insignificant predictors, notice that my coefficients stayed pretty stable. The values here are very similar to the values here. Pretty stable. And then when I dropped out work hours per week, they still stayed pretty stable. Not much change is going on. Now recall that there was a 0.77 correlation between diet and exercise. And when I drop out diet, then this changes quite a bit. It changes from 0.066 to 0.092. But overall, the stability of these coefficients as you move through dropping terms is an indication that the input variables are not so highly correlated with each other that it really is causing big distortions in our regression coefficients. Now, let's go look at an example where we really have high correlations between variables. In this case, I've gone to a different model, and really all I have in here is I have average daily exercise and what percentage of the time they adhere to their diets. Now, if you look here, you can see that this is our outcome variable. How much percent body fat did they lose? If you look down at their daily exercise and how well they adhere to their diets, there's very good linear relationships with the outcome variable. And if you look at the correlations amongst these input variables, then you can see that the correlation between daily exercise and diet adherence is 0.9251. So this is very strongly collinear, and we have exceeded our rules of thumb where we're going to get a lot of distortion because we have a correlation between input variables that is up around 0.9. So here's when I put both exercise and diet in the model. You can see these coefficients, and I've just copied them down here. And then when I dropped exercise, you can see that diet grew a lot. And then if I took diet out and just left exercise in, then exercise grew a lot. So what's happening is when you put both terms in and they're very, very highly correlated, they are sharing some of what they're predicting. And so these are sort of distortions. They're not really accurate estimates of the contribution of diet and exercise. And we know this because as we drop these terms out, then this changes quite a bit. Or if we drop this term out, then this changes quite a bit. And so this is a good example of how the betas become unstable when you have input variables that are so highly correlated.